dropping off on a gentle, what we call a ramp, which is, well, you know what a ramp is. Anyone who's ever seen a wheelchair ramp knows it's a gentle incline. And there's a gentle incline down to a narrow basin that we call the Seabree Trough, which really here, we're still on the border of it. This is meant to be black shale up here. So you're going all the way from sort of typical looking Cincinnatian, especially during the Cope interval, to a gradation, more and more gray shale, and finally, as even Ulrich recognized, dark shales up to the north. This was a deeper water area, and it was sloping off. And we have this interesting interplay between the limestone, which is being generated by local shells, the homegrown stuff, and the muds and silts that it seemed to be at this time probably really coming in from this direction, the muds at least, from the northeast Taconic Mountains. Some silts, however, seem to have come in from this direction. Well, that's a fine point for you. So one could look at this whole region, even over an area where there's some change in environment, going from shallower to deeper, and say, and I got very interested to see, well, you know, if you really take the transect along the AA highway, going from Cincinnati to Maysville, you do find certainly that while some of the details vary, even within the scale of an outcrop, as you well know they do, but yet if you look at the bigger packages of limestone and shale, they don't have to be too big, maybe only 20 centimeters thick, that you can trace those things over this region. So I've simply marked in gray here the thicker shale intervals, because that was the first thing. Try to find thicker shale intervals that you could trace, and they do stay as thicker shale intervals between Cincinnati and Maysville. Then you could start to interpolate in between all the little beds, and then I started going after more detail, looking at, for example, especially up in the Alexandria cycle. Let's see, where am I here? That's around this suite up and through here. You start to really see some fine details, like little beds of peculiar fossils, even peculiar preservation of trilobites or so. I'll show a few examples. That can be then additional tests to see if you're getting it right. And when you start to see not just one bed that looks the same, but you see a pattern of maybe 10, 20 beds that are in the same, they're each unique in some way, and are stacked in the same pattern, then you say, my heavens, you really are tracing out a quite detailed layer cake in the Cincinnati area. What about dear old Ulrich, who probably was not only vilified because of what was thought to be an antiquated notion about him, but he was a tough guy. I think he was a difficult man. But nonetheless, I am something of an Ulrich champion, because I think he got a lot right, actually. And I think he was too much blind. Anyway, sorry. Let's get back to thinking about some other things. Storm processes. We all think, I guess, that storms have something to do with these beds. And I just wanted to point out that what sort of goes on during a major tropical storm, a hurricane? Well, there's several things that go on. First of all, you have a barometric effect. Very often, there is a higher pressure out over the sea than in on shore, and this causes what's called setup. It washes water up the slope, so maybe this is the Cincinnati ramp coming down from Lexington into the Seabree Trough. Let's just say that it is. And you could pile up water in the shallower areas to the south in this place. It's called setup. The wind tends to blow on shore also for the same reason, and that further piles things up. Wind blows more strongly during the hurricane, but sometimes rather chaotically. As you know, the hurricane is a rotating cell, so it's not always exactly the same direction. It's actually shifting around. But the net effect of a lot more wind is a lot bigger waves. And what really matters is the wavelengths, the spacing of those waves. They get to have big, long wavelengths. Now, there's an interesting relationship. The longer the wavelengths of these big waves, the deeper down those waves affect. So the waves which would normally affect something like 15 meters or 10 meters, let's say, 30 feet down, now can affect things that are maybe 50 meters, 100 some feet down, 150 perhaps down on the seabed. This is called storm wave base. And the storm wave base drops from the normal position during fair weather down to some much deeper position where it can start to touch down on the bottom and start to stir things up, move things around, and so on. Now there's one other thing that you should be aware of that happens during the storm. You see all that setup of water on the coast? It's got to go somewhere. it's getting pushed up on there. Yeah, you know, this could be a really major problem in a coastal city like Galveston. You probably know one of the biggest disasters ever in North American history is Galveston. We had a coastal setup, storm surge it's called, and you know that was associated with a high tide. Wow, that's like a perfect storm, and you get things inundated. But that water ultimately has to go somewhere, and it squirts back down under pressure in what's called a gradient current. Theoretically, it's trying to roll back down the slope to sort of continue the circulation pattern. Now, lots of things are going on during this. You're getting stirring up of the bottom, so in shallow water areas, coarser sediments will tend to accumulate, whereas the finer grained sediments will be, as we say, winnowed out. It's like taking away the fine grained stuff. And where does it go? It gets carried in the gradient currents to be distributed further down slope. So the shallower you are, typically the coarser the sediments, the more stacked are the storm beds, stacked one on top of another. And they should get more muddy as you go down towards wave base. And you find maybe the more distal or distant effects of storms are siltstones, or maybe even just muds, clays that fall out associated with the dying out end of the storm. So this is part of the backdrop of our Cincinnatian beds. Most everyone would say, yes, this clearly has a role to play. This is a very odd diagram because it's so extraordinarily distorted. This means about maybe 1 meter, maybe a couple feet, 3 feet. Down here it's getting thinner to 20 centimeters or something. But this distance is meant to be perhaps 100 kilometers out. So it's a very distorted diagram. But what it's really showing is that for any given set of storms, you should produce graded, coarse, gravelly beds. And in this case, what's going to be the gravel? It's going to be shells, typically. Sometimes rip up mud pebbles. As we go further down slope, though, it'll get finer grained. You'll get graded beds with only shell hash in the bottom, and then you can get these little laminations. And this can yield also what we call hummocky cross-stratification. It's not a big deal, but it means the interaction between the waves and the currents produces a swirly pattern that's recognizable to us. And eventually you get down here, it's just a thin silt layer with some mud coming out the end of the storm. The mud drops out, and out here maybe just a mud layer. So we have a spectrum of things that can happen or be deposited during a storm, from just distant muds to these gravels of shell hash and so on. So that's the basic storm model. Now I'll get back to these cycles again. And here's where the difference between my view and Steve's will, I hope, become eventually apparent. But here are limestones. They're shell hash beds. They show sharp bases, so they have ripples on their top, that's for sure. And so it's very likely, you can see in that really the orbitals of a wave. And so these do represent sediment that was processed by waves, storm waves. And so many people looking at the Cincinnatian have always said, well, the muds represent background times when things are quiet and between storms. And the shell hash beds, well, they represent storms. But long ago, people began to realize it's not quite that simple. When you look at the thickness of these shell beds, and you look at the complexity of them, the way they split and come back together and form different pods and lenses, you realize it isn't quite as simple as just a single storm. Although I've got to say, in some cases, the last huge storm, the perfect storm, sometimes worked over that sediment one last time and put the ripples and things like that into it. Well, that doesn't mean the sediment was all laid down or initiated during that one storm. A lot of it may have been kicking around for a long time. I'll get back to that. Now let's get back to the cycles. Okay, let's the cycles. Here's a nice example. 29 to 30. You've got a limestone. You've got sharp contact below it and above it, and then you've got a shale, and then you've got another limestone. So that's a cycle. There are cycles at different scales. I might point out. For example, here you're kind of at the top of a bundle where they're close together. It's 28, 29, 30. Then you've got a big shale, and here's where I diced off and made submembers of the coat because you can find these big shales. Okay, so that's something. So there's cycles at least two different scales. There are the little ones, and then there's this bigger scale marked out by the great big shales. But again, mostly people said, well, what those represent is an alternation between storm-deposited stuff and non-stormy times. And according to the most popular model, Model 1, that I'll put here, which is advocated by a lot of people, including Steve Holland, although he's also saying, there's more to it than this, is that what you have, when you get to shell beds, it's not just one storm, but a lot of storms, okay? But it's an alternation of a time when you get more storminess, stronger storms, or just more numerous storms that are touching down more often to produce the shell hash bed. Sounds good. In the context that we know that storms were around, it's the right kind of latitude setting for storms, it sounds good.